I know I haven't been updating in a while, and I thought I'd share a recent insight on the number I. Specifically, it is actually about the theoretical number of I to the power I. Now, in order to understand this, we need to use Euler's formula, basically, which, if you've seen my series on the natural logarithm of 1, which I hope you have, you'll understand why and how e to the I theta equals cosine theta plus I sine theta. Which is arguably, in my opinion, the greatest formula of all time that has been developed as of yet in mathematics. Now, hopefully, you also know that I prefer this special number, sometimes referred to as eta, this Greek letter eta, being equal to pi over 2, so 1/2 pi, as being a circle constant, being used as a circle constant, rather than just pi. And we mathematicians naturally want to substitute eta, or pi over 2, in order to get, and you may already be familiar with this, e to the I eta equals, well, in this case it's cosine pi over 2, which is 0, and plus I sine pi over 2, well, that's I times 1, if we look at the unit circle. And so we simply get this is equal to I. So this quantity, e to the I eta, is precisely equal to I. Just another way of expressing it. Now, with this simple, kind of simplified formula, we can actually raise both sides of this equation to the power I. So we get e. Actually, let me just write something here. I'm just going to signify or raising both of these to the power I. So theoretically, we can raise I to the power I and simplify this. We basically get, and we can use this exponent, of course, as basically a factor. It's just a law of exponents, basically. So we can say e to the I times eta equals I to the I. Now this is where it gets very, very interesting. We can say e, and we know that, well, I times I, or I squared, is -1. That's how it's defined. So we get negative eta, and I'm going to write that as actually pi over 2 in this case, because we know eta is equal to pi over 2. So I'm just going to write that in a more familiar way, is equal to I to the I. And so this is amazing as it is. This is astounding. We basically know for a fact now that the quantity I to the I is equal to this very simple quantity, this real number. We can even call this a real number if we like, a computable real number. Actually, I'm going to write this in a more a way that you might enjoy even more, because to make it more simplified. It's a negative exponent, so we just say 1 over e to the power over 2, and if we have pi over 2, if we have a rational exponent, then we can kind of pull out the denominator, in this case 2, and make it into a radical. So in this case it's square root, so 1 over the square root of e to the pi. And that is amazing. See, this wonderful number, this transcendental number, which is real. It's contained within, I mean, it's computable. It's something in the real number system. So something that we can compute, in other words, approximately compute it. Now, these are rational numbers we're dealing with, e and pi. But if you think about it, this is quite beautiful. This is amazing. 1 over the square root of e to the pi. It has a wonderful ring to it. In fact, I think this has become one of my favorite numbers of all time, really. And if you look it up, you will discover that this is indeed a transcendental number, which is perhaps not surprising. E and pi are both transcendental after all. But yeah, it's very cool. So I to the I is real, and we know that for a fact because of this quick little demonstration. It's very, very interesting. But it doesn't just end there. What I tried to do after this, in order to extend this, I found another interesting pattern that I'd like to share. On a more general note, what I'll basically be studying is what is I to the quantity of I to the n for varying values of n. Actually, yeah, I'll start with n equals 0. And in this case, we basically, as you can imagine, we simply get I. Because I to the 0 is 1, and I to the 1 just I. Then as we move on, and say n equals 1, well, in that case we get what we just talked about, I to the I. And in that case, we know that is e to the quantity negative pi over 2, or one over the root of e to the pi. And that is the square root. Now for n equals 2, basically, well, in that case, I squared is negative 1, so we're talking about I to the negative 1. You may recall it's actually equal to negative I, and there are multiple ways of demonstrating this. One of which is to say, this is basically 1 over I, or 1 over the square root of negative 1, which really, if we just rationalize it, we get root negative 1 over negative 1. Which is really negative I. And another way of thinking of it would be, well, as we said before, e to the I pi over 2 is equal to I. So if we raise each of these to the negative 1 power, then we actually get e to the negative I pi over 2 being equal to I to the minus 1, which is, if you think about it, equal to cosine negative pi over 2 plus the sine of negative pi over 2. And in this case, using the unit circle, we can find out that this is 0, and I'm sorry, this is I sine. Plus I sine of negative pi over 2. Negative pi over 2, if you take the sine of that, that is negative 1. So we do get negative I. Now for the case where n equals 3, things get quite interesting. We basically know that e to the negative I pi over 2 equals negative I, as we just stated. And so we can raise each side of this equation to the power I, and so what we end up with, because we can use this exponent, and make it as a product, basically bring it down to be a product of this exponent of this quantity. So just as we've done before, we basically say, well, it's negative I times I, which is 1, and you can verify that. You can say it's It's basically -1 times I, basically. Which is -1 times -1, so it's simply +1. And the work shown there, I can write this out for you. It's e to the -1, because we're kind of factoring out a negative. We have this e to the -I, so just focus on this part of it. -I, we'll just think of it as -1 times I. And then there's this I, which we're making a product, basically. We're bringing this exponent down, in other words. And you make it, so there's another I here, in other words. And it's times pi/2. And as I was saying, I times I is -1. So this is -1, and -1 times -1. Basically, it all crosses out. And we get e to the pi/2. Now, that is something very fascinating and something we're familiar with in the computable number system, the real number system, basically. And we have the quantity -I to the power of I on the other side of the equation. Now, I'm going to zoom out, and I'm going to work on the right side of the equation. And so, basically what I say is, we can express this right side of the equation in another way. And we can say quantity -1 to the I, so in other words, we can think of -I to the I as being -1 times I, this whole quantity to the I. And then we can distribute this exponent to each term. So -1 to the I times I to the I. And I to the I is something we've already constructed. It's something we've already determined in the case where n equals 1. You can verify that it's e to the -pi/2. That's what it's equal to. So, therefore, looking at this equation as a whole, we can substitute e to the -pi/2 for I to the I. And then what we get is this right here. E to the pi/2 is equal to this quantity, -1 to the I, times e to the positive pi/2. Now this is this is extremely interesting. This is astounding. Because basically, what this means is we can solve for this one quantity, which I highlight over here, and the quantity -1 to the I. Now people often don't think about what the quantity -1 to the I would be equal to. But it actually has a meaning. It has a very wonderful, marvelous meaning. And you can probably see where I'm going with this, because we can divide each side by this factor, this e to the -pi/2. Sorry, e to the -pi/2, right? And so therefore, in our final step, we show that the quantity -1 to the I equals, and then these have the same base, so we can simply say, using simply law of exponents, we can say this is simply equal to e to the quantity pi/2 minus -pi/2, or pi/2 plus pi/2, therefore it is e to the pi. Now, I find this to be astounding. It's really quite marvelous. I hope you enjoyed this this short video, and have a great summer. And let me know any feedback you have, or any personal insights or ideas that you have on exponentiation of I, or any way you can extend this further. So I'll see you later. Thanks for watching. Well, I just realized, kind of an error in what I've just described. This is a bit confusing, because as I've said before in my log of 1 series, exponential functions are cyclic. So, in other words, the function e to the x, when we introduce imaginary numbers, becomes cyclic. So it takes on, it becomes more like a sine or cosine function, where the values that it returns are repeated, in other words. So this is more complicated than I had thought, and I think what I say is technically accurate, but it's not the complete truth. So, I am right in saying that negative I to the quantity I equals e to the pi over 2. That, at least, is correct. But if we kind of just ignore that just for the moment, because this is true, we know this is true, I'm going to do something else. I'm just going to say negative 1 to the I. If we really want to know the value of negative 1, that quantity to the I, I'm going to set this equal to q. And a method that has proved rather reliable up till now is raising both sides of an equation to some constant. So I'm going to raise both sides to I, as I have been doing. And so what we get is negative 1 to the I equals q to the I. And that seems perfectly fine, and we can kind of combine these two exponents, because we have this quantity of negative 1 to the I, and we're raising that to a power, so we can multiply these together. And I times I is simply negative 1. So this is what we get after that. And after that, then we get, well, negative 1 inverse. The multiplicative inverse is just itself. Therefore, negative 1 equals q to the I. And so from this, we can pose the question, using Euler's formula, what number returns negative 1? And the answer to that question, as you probably already know or can figure out, is indeed e to the I pi. Now, e to the I pi, and if we're kind of factoring out an I from that exponent, we can simply get, e to the pi to the I equals negative 1, and we know that to be true. If you're thinking about it in terms of the fact that e to the x is cyclic when we introduce imaginary numbers, then we know the answer is not just pi here. We could have something else. We could have pi plus or minus 2k pi. And I'm saying 2k pi because 2k pi is a pretty common thing you'll see when talking about the unit circle, because it's one full rotation, or any integer multiple of a full rotation. So any integral number of rotations, full circle rotations, if that makes any sense. And I'll try to add an image to make this more clear. I'm fairly sure that q would equal e to this quantity. Therefore, this, right here in brackets, is actually the meaning of negative 1 to the I. Now, feel free to correct my work again. I think I made a mistake to begin with, and that's what stirred this, these insights. Got something wrong, at least according to Wolfram Alpha. But then again, that's the same source that tells you log 1 equals 0, so who knows? I might not be too far off. Anyway, thanks for watching / listening.